Hello everyone, I'm Weiyu. Today I will be presenting our work learning instance-level N-Ary semantic knowledge at scale for robots operating in everyday environments. Robust operation in everyday human environments requires robots to effectively model a wide range of objects. Perceiving and understanding semantic properties of objects is useful for many real-world tasks, such as searching for objects or interpreting vague human instructions. Prior work has encoded semantic knowledge primarily as pairwise relations between an object's class label and its semantic properties, such as cup is made of glass. These semantic properties can come from a variety of perception methods and be grounded in different sensory modalities. However, a binary representation fails to take full advantage of multimodal observations because it ignores the complex relational structure between various object properties. For example, in a pairwise representation, observing that a cup is in cabinet does not help to infer whether the cup is clean or dirty. Our goal is to enable robots to collectively reason about object properties, particularly ones grounded in different modalities, and to predict semantic properties of objects based on partial observations. We introduce a novel semantic reasoning framework that uses N-Ary relations to model complex interrelated object properties. This framework enables the ability to reason at different levels of abstraction. For example, a robot searching for a cup with no additional information is able to perform class-level inference to identify both the cabinet and sink as likely locations. Given additional information, such as that the cup is clean, N-Ary relations help predict that clean cups are more commonly found in cabinet rather than in sink. A key challenge is to collect semantically meaningful N-Ary data. In other words, we need to know how often various attributes co-occur. Our solution was to learn N-Ary relations from observations, each representing a set of identified semantic properties of an object instance within a particular environmental context. We use a multi-step crowdsourcing process to collect this data, the details for which can be found in our paper. We introduce a transformer-based neural network to mine generalizable patterns from these observations. Our transformer takes as input embeddings of properties observed from an object instance and builds a contextualized embedding for them. The contextualized embedding is then used to predict unknown properties. To train our model, we randomly hide a single property from observed properties with a mask value and requires the model to reconstruct the hidden property. In this example, we require the model to reconstruct the location of this blue cup in the sink. Trained with this self-supervising objective on different properties and different object instances, the model will learn N-Ary relations and can be queried directly to retrieve N-Ary knowledge or used to predict unknown properties of novel objects. To facilitate learning multimodal properties of objects, we contribute the semantically richest dataset to date, consisting of 1,457 object instances categorized into 11 object classes, modeled by 200 properties organized into 15 property types. We compare our method with 5 different baselines in predicting unknown properties of object instances. Compared to the top performing baseline, a Markov Logic Network, MLN, our method shows significant improvement while reducing computation time by 150 times. We validate our methods in a real-world robotic tasks, where the robot needs to predict locations and rooms of objects based on a sparse set of properties human users would normally provide. For example, find a clean glass cup or find a cold beverage. This experiment validates our model with a different set of users than the users who help construct the link data. Compared to the baselines, our model is the only model that can approach human-level performance at retrieving an object from users' top 3 locations within 2 tries or 3 tries. We also demonstrate the qualitative improvement. Equipped with our model, the robot is able to find objects considering different properties of objects. In this example, the robot searches for a dry sponge on kitchen counter and in the drawer, while tries to find a wet sponge in sink. In summary, we address the problem of predicting semantic properties of objects based on partial observation. We introduce a scalable transformer model that generalizes N-Ary relations from data and can perform inference at different levels of abstraction. our model helps robots better understand objects in the real world.